Good morning, everyone. Thank you for being here today for our live webinar, A Paradigm Shift in Electrocatalyst Synthesis. My name is Andrei Linka. I am content creator for VS Particle, and I will be your guide through today's live session. The duration of this webinar will be between 40 and 50 minutes, including the Q&A session. Presenting today is our colleague Wilbert Vrijburg, PhD and application specialist. Before we move on to the topic of the day, I would like us to take a few moments to go through today's agenda. We will discuss handling questions during the presentation, webinar recording, and upcoming events. I will then provide you with a few ways for you to get in touch with us with a short VS Particle introduction for the people who are not yet familiarized with what we do, before we move on to Wilbert, who will showcase the flexibility of our technology and how its adoption can simplify the preparation of model electrocatalysts and accelerate the discovery of novel electrocatalyst compositions. The last part of today's session will be reserved to answering your questions. We do encourage you to ask questions during the webinar, and we will try to answer all of them after the presentation has ended. However, for the questions that remain unanswered, we will follow up with an email in the coming days. You can find the chat room in your bottom right corner, the icon with the question mark. Please don't forget that you are on mute during this session and you won't be able to speak. So any feedback, remarks, and questions you might have, please use the chat room for this. This webinar session will be recorded and we will soon send you a link in the coming days so you can share it with your colleagues or watch it later. We have two more upcoming live webinars, Developing and Enhancing SIRS Substrates with VS Particle Technology and Accelerating Gas Sensor Composition Screening with the VSPP1 Nanostructured Material Printer. We will soon announce the dates for this webinar, so keep an eye on our website and our social media. We are happy to provide additional information, and there are multiple ways in which you can get in contact with us. If you would like to know more about VS Particle solutions and how they can help you in speeding up your research, you can check our other application pages at www.vsparticle.com/applications. Or if you are interested in trying out VS Particle technology, you can request a demo and try it in the safety of your own lab by using the form available at www.vsparticle.com or through email at demo@vsparticle.com. And for any other information, you can always contact our sales department, sales@vsparticle.com. VS Particle is a spin-off company of TU Delft, located in the Netherlands, with over 20 years of experience in the synthesis of aerosols and with a young and passionate team of scientists and engineers. VSP is unlocking a whole new world of possibilities at the nanoscale. As we all start to understand these possibilities, it will enable research and industry to rethink production processes and develop new materials to create innovative applications. We develop and commercialize completely new technology to automate the production of new materials, and we are key nanotechnology providers in different fields like catalysis, semicon, and health. Since 2014, we have helped scientists and industry all over the world to drastically reduce the development time of new materials and products by enabling automated nanoparticle production. At VS Particle, we provide products enabling the production of nanostructured materials for fundamental and applied research based on a simple to operate and scalable principle. And here you can see a layout of our current product portfolio. Thank you for bearing with me through this short introduction. I will now hand off to my colleague Wilbert, who will do the presentation of today's topic, and I will talk to you at the end of the presentation when I will take your questions. Please don't forget to leave your email in case you don't have a Teams account, so we are able to reach you. I hope you enjoyed this presentation and I'll talk to you in a bit. Wilbert, you have the floor.
Well, thank you, Andrea, for the kind introduction. Hello, everyone. My name is Wilbert Vrijburg. I'm an application specialist at VS Particle, and today I'm presenting from Delft in the Netherlands, and I'll be presenting the accelerating of electrocatalyst synthesis and composition screening via spark ablation. So electrocatalysis today is really a rapidly growing field with strong academic and industrial relevance. And one of the major driving forces behind this surge of interest is the need for us to mitigate climate change and transition towards clean, efficient, and sustainable energy sources with effective storage solutions. In addition, the electrification of our chemical industries has made the development of efficient electrocatalysts even more important. Furthermore, several recent studies have demonstrated the wide-ranging applications in which electrocatalysts are employed, with some of the most relevant ones including CO2 valorization, water electrolysis, and fuel cell applications. However, one of the biggest challenges that is facing the electrocatalysis community, and something that we need to overcome, is the significant catch-up that electrocatalysis needs to play with respect to classical heterogeneous catalysis, which itself has seen incremental improvements in understanding and performance over the space of the last 150 years. So for this reason, there is a need to screen a vast array of potential material compositions to obtain novel electrocatalysts that are highly active, stable, cheap, and industrially scalable. Now, if we look at the one of the bottlenecks that electrocatalysis is currently facing, it's really the preparation methods that are employed within the field. And the current preparation methods are, by and large, wet chemical approaches with a wide variety of approaches. But what they have in common are that there are multiple steps. And in each of these steps, we introduce new changes, or we introduce changes into the final material. So firstly, there is the preparation of the active phase, which is a multi-step process, and then the application of the active phase onto a substrate or an electrode, which is also a multi-step process. And overall, the main drawbacks are that these approaches are cumbersome, time-consuming, and because of the number of steps, there are always going to be reproducibility issues. So we've spoken to researchers within the field of electrocatalysis to get an understanding of what it is that they're looking for. And we found that researchers would like to develop synthesis methods that can allow PhD students to focus on electrocatalysis research and not on synthesis. They would like to develop synthesis methods that can quickly and reliably prepare reference electrocatalysts. And finally, and this is also important because of the catch-up that electrocatalysis needs to play with heterogeneous catalysis, there is a strong desire to accelerate the discovery and optimization of new electrocatalyst compositions by screening their performance under industrially relevant conditions. So what I hope that you will get out of this webinar is that you will have a basic idea of what our technology is based on, namely spark ablation, and understand the flexibility of this approach. I'd also like you to understand how our technology can simplify the preparation of model electrocatalysts. And I hope that you understand how our technology can accelerate the discovery of novel electrocatalyst compositions to meet our future sustainability demands. So with that, here's the outline of the remainder of the webinar. To begin with, I'll present the VSP G1 nanoparticle generator and also explain a bit about how spark ablation works. Attached to that, we have our VSP accessories, which combine with the VSP G1 nanoparticle generator. And I'll also discuss a use case scenario in which we prepare a single electrocatalyst using one of our accessories. And then finally, and then this is really the part where we try to showcase how we can accelerate electrocatalyst synthesis and screening. I present the VSP P1 nanostructured material printer with a use case of high throughput electrocatalyst screening. But first, the VSP G1 nanoparticle generator. So in principle, in order to, so our G1 nanoparticle generator uses spark ablation to prepare nanoparticles. So what you need for that are two electrodes made of a semiconductive material or a conductive material, such as a metal, and an inert gas, such as argon or nitrogen, which will take the nanoparticles away from the electrodes and then bring them downstream. A voltage is applied in between the two electrodes, and the entire process can run at room temperature. So once we apply a voltage between the two electrodes, we get a spark, and this spark ablates or evaporates a small amount of the surface atoms on the two electrodes. And what you get is a vapor of your electrode material, and this gradually sinters towards atomic clusters and then larger particles. And these larger primary particles can then aggregate or agglomerate to form even larger particles. So your output overall are pure ligand-free nanoparticles with a primary particle size below 20 nanometers. And we're able to obtain larger nanoparticles by aggregating these primary particles. Overall, the ablation rate here is within the range of milligrams per hour, but this is really dependent on which element your electrodes are made out of. So this varies between a couple of milligrams per hour to tens of milligrams per hour. So what does this look like in our VSP G1 nanoparticle generator? So here on the left, we have a user of our G1. Here's the base unit of the VSP G1 nanoparticle generator with a dial for setting the current and a dial for setting the voltage. We have our gas inlet here on the left, and then in the reactor head, we have our electrodes where the nanoparticles are generated and the spark is generated. And we have our gas outlet on the right. So if we zoom into the reactor head, again, we have our gas inlet here on the left with our inert gas. Here we use hollow electrodes, and in between these two electrodes, we get a spark that forms, and then you get a vapor of your desired material, which then agglomerates or aggregates to form larger clusters and larger primary particles, and then larger agglomerates and aggregates. Now, what is really unique about this technique is we can readily vary the average particle size by varying the residence time of the ablated material within the reactor head. So in essence, by increasing the gas flow, you shorten the residence time, which should then lead to the preparation of smaller nanoparticles and vice versa. A lower gas flow will increase the residence time within the reactor head, which leads to more aggregation and therefore larger particles. An added flexibility of our technology is the ability to really have a wide range of material compositions. So on the left of this solid green line, I show you the types of materials that can be prepared using a single G1 nanoparticle generator. If we equip the nanoparticle generator with electrodes of the same element, we get monometallic nanoparticles. If we mix and match the electrodes, we're able to get alloys with, let's say, a varied composition between the two extremes. But if we pre-alloy our electrodes, we're able to get nanoparticles with an elemental composition that aligns with the composition of the pre-alloyed electrodes. In addition, if we combine multiple G1 nanoparticle generators, we can prepare a wide range of materials depending on how we connect the two nanoparticle generators together. So if we have the generators in sequence, we can deposit layered materials, so nanolayers. If we have the nanoparticle generators in series, we're able to prepare core shell or decorated nanoparticles. And finally, if we have the two nanoparticle generators in parallel, we're able to prepare, again, alloyed materials. In principle, any conductive or semiconductive material can be used in our G1 nanoparticle generator, provided that the material can be pressed into an electrode that we can then place in our nanoparticle generator. This is roughly what it looks like. So here on the end, we have an electrode of a certain material, and we can click this electrode into the end cap of our reactor, and then you're pretty much ready to start sparking and preparing your nanoparticles. We have four main deposition methods: diffusion, filtration, impaction, and printing, and I'll get to these throughout the presentation. The first three deposition methods are covered by the VSP A series deposition accessories, and the final deposition method, printing, is covered by the VSP P1 nanostructured material printer. But first, the VSP accessories. So here on the left, we have the VSP G1 nanoparticle generator, and we have three accessories that come alongside that. And if you combine the two, we're able to prepare nanoparticles in a wide variety of substrates. The markets in which we see this equipment being relevant are catalysis, sensor development, healthcare, energy, and filter development. The three deposition methods that we cover here are diffusion, filtration, and impaction. And the accessories are also numbered accordingly. So 1 is diffusion, 2 filtration, 3 is impaction. So first we discuss the diffusion, the VSP A1. So here on the left, we have the VSP G1 nanoparticle generator, and on the right, we have our diffusion accessory, the VSP A1. We'll have a gas inlet here on the left, which collects the nanoparticles that are generated in the spark. And these are then transported to the VSP A1 diffusion accessory and deposited on a substrate that's within a sample holder. And then we have our gas outlet here on the bottom. The A1 connects directly to the G1 using a swage lock connection. So the A1 diffusion accessory is compatible with flat or 2D substrates with a maximum size of 10 by 10 millimeters. We're able to obtain surface coverages between 1 and 10%. And we see it really being relevant for in situ TEM, in situ spectroscopy, electrocatalysis, and material science research. Common substrates that have been used are TEM grids, silicon wafers, and coated wafers. I provide two examples for this accessory. The first one is the preparation of in situ TEM samples. This work was done in collaboration with Professor Gunther Rupprechter of the TU Vienna in Austria. After 30 minutes of deposition using gold electrodes in our VSP G1 nanoparticle generator, we're able to deposit gold nanoparticles on a TEM grid in the diffusion accessory. And we were able to obtain clean, surfactant-free nanoparticles. And what you can see here from the HADF STEM image are really small crystalline gold nanoparticles that were deposited easily on these TEM grids. A second application is was done in the group of Professor Bert Weghuizen of the University of Utrecht here in the Netherlands. They sought to study nickel-based catalysts using shell-isolated nanoparticle-enhanced Raman spectroscopy, or SHINERs. And they wanted to get nickel nanoparticles on gold encapsulated by silica particles. They compared three approaches, so spark ablation and then more conventional approaches such as colloidal synthesis and impregnation. And what they found was that for their Raman studies, the spark ablation prepared samples were the only ones that were Raman active. And this was really the first example of using a low transition metal in a SHINERs application. And this work was published earlier this year. Secondly, we have the VSP A2 filtration accessory. So here we have the nanoparticle generator, and using a swage lock connection, we're able to connect it directly onto the filtration accessory. We have our gas inlet on the left, which collects the nanoparticles that are prepared in the spark, that are then deposited in the filtration accessory. And then we have the gas outlet here on the right. The substrates that we're compatible with it can have a maximum diameter of 47 millimeters. And what's really important, of course, since it's filtration, is that the substrate needs to be porous. Applications in which we see this being relevant are electrocatalysis, photocatalysis, in situ spectroscopy, and the preparation of unsupported clean nanoparticles, and ground-up electrocatalyst synthesis. Common substrates that can be used are just filter paper for if you want your clean nanoparticles, carbon cloth, and metallic meshes. The final accessory is the VSP A3 impaction accessory. Again, we have our G1 nanoparticle generator, which connects to us with a swage lock connection to our impaction chamber. We have a gas inlet here on the left, which collects the nanoparticles, and then we have our substrate holder here in the impaction chamber. And in order to get a hypersonic beam to deposit these nanoparticles with impaction onto a substrate, we connect the impaction chamber to a vacuum, and then we also have our gas outlet here on the left. This image here shows roughly what the inside of the impaction chamber would look like. The vacuum is able to prepare a hypersonic beam, which then focuses the nanoparticles through a nozzle, and then we can impact them onto a substrate. We can adjust the spot size up to 3 millimeters. We're able to prepare metallic and metal oxide species and layers. And the operating conditions are just room temperature and 0.1 millibar because, of course, we're working under vacuum. Applications are that we can use the impaction chamber as a standalone unit, but it's also implemented in the VSP S1 size selector with common substrates, including silicon wafers and TM grids. Now we get to our use case, and what we looked at here was the preparation of a single electrocatalyst for the oxygen evolution reaction, which is a very relevant reaction today. So the general setup that we use is a VSP G1 nanoparticle generator with a VSP 8.2 filtration accessory. In the nanoparticle generator, we equipped it with 2 iridium electrodes. We varied the voltage between 0.5 and 1.3 kilovolts, and the current was varied between 1.0 and 10.4 milliamps. The gas inlet was either argon or nitrogen, and we varied the flow between 1 and 15 liters per minute. A titanium felt was used as a substrate, and we deposited for between a few minutes to a couple of hours. What's important is because the titanium felt is square, we used a mask to focus the nanoparticles onto the substrate so that you can really deposit on a different shaped substrate, so it doesn't just need to be circular. This work was done in collaboration with an industrial partner. So here are the initial results. Here on the left, we have our titanium felt with iridium nanoparticles deposited on it. But what's known about the OER reaction is that the active phase are iridium oxide nanoparticles. So here on the right, we have the titanium felt with iridium nanoparticles after an oxidative treatment at high temperature in synthetic air. The performance of these materials was studied using cyclic voltammetry. So first, to show you the performance of the bare titanium felt, what we find is that the bare titanium felt only demonstrated minor oxidative and reductive processes as we swept from lower to higher voltages and then back. And this is really down to the oxidation of your titanium to form titania or titanium dioxide. And as we sweep from higher to lower voltages, we reduce our titanium oxide to form a titanium hydroxide species. Now, after depositing iridium on the titanium felt without a pretreatment, we find that there are 3 additional reductive steps that we observe. The first one is the reduction of oxygen to form water. The second one is the reduction of hydrogen ions to form adsorbed hydrogen atoms. And the third one is the reduction of hydrogen ions to form hydrogen gas. So what we've shown here is that we have a hydrogen evolution reaction electrocatalyst, and this process can be ascribed to the presence of metallic iridium on the titanium felt. So this really showed that we prepared and deposited metallic iridium nanoparticles on the titanium felt. Next, a high temperature oxidative treatment was carried out, and what we find in the cyclic voltammogram is that the reductive processes are completely gone, so we don't have any more metallic iridium on the felt. And as we sweep from lower to higher voltages, we observe an oxidative process, and this is really the oxidation of water to form oxygen. So what we have here is an oxygen evolution reaction electrocatalyst, and this can be ascribed to the presence of iridium oxide nanoparticles on our titanium felt. So just a basic summary of this section or of this use case. We've demonstrated that titanium felts can easily be modified with iridium using the VSP G1 nanoparticle generator equipped with the VSP A2 filtration accessory. After an oxidative treatment, we were able to obtain iridium oxide nanoparticles on the titanium felts. And although what we've shown here is that the metallic and the oxidic iridium on the titanium felt, they behave as expected. What we really show here is that this approach can be employed to easily produce reference electrocatalysts. And this is then not only with iridium, we can prepare these reference electrocatalysts using other metals as well. The next challenge then becomes, how can we employ VS particle technology to accelerate the discovery and screening of new electrocatalysts to meet the demands of a sustainable chemical industry powered by renewable energy? And for this, we need to use the VSP P1 nanostructured material printer. So here we have the VSP P1 nanostructured material printer. On the left, we have the G1 nanoparticle generator. Again, we have the gas inlet on the left, collecting the nanoparticles. Here we have, on the right, we have the VSP P1 printer. There's a substrate holder at the bottom, which is on an XYZ stage so that it can move. And that's where you will place your substrate. The nanoparticles are deposited via a print nozzle, and the entire chamber is under vacuum. So the printer uses inertial impaction to deposit the nanoparticles on a substrate, which is shown here nicely in this diagram. We can deposit between 0.1 and 1 centimeter spot sizes. We have a deposition accuracy of 10 micrometers, and we have an XYZ stage, so we can really pattern these nanoparticles onto a wide range of substrates. In addition, by varying the deposition time, we're also able to control the layer thickness. Now, the maximum size of the substrate that fits into our printer are 15 by 15 centimeter substrates, and we can deposit on MEMS, SIRS, 6-inch wafers, and flexible polymers. Here are some examples of materials that have been prepared using the printer. Here on the top, we have a copper oxide nanoporous film, and at the bottom, we have a gold nanoporous film that was prepared using our printer. So now the important use case, how can we use the printer to screen electrocatalysts in high throughput? For this work, we collaborated with Dr. Klaas-Jan Schouten here in the Netherlands. He is a part-time assistant professor at the University of Amsterdam, but he's also a full-time employee at Avantium. And Avantium is a company based in Amsterdam, and they offer systems and services for catalysis research, but really their core expertise lies within high throughput catalyst testing. Now, Dr. Klaas-Jan Schouten is part of the VOLTA program, and in the VOLTA program, they seek to convert CO2 to high value chemicals via electrochemistry. So there's a strong desire to develop high throughput electrocatalyst screening methods, and for this reason, we work together on this project. So at Avantium, they were able to develop an 8x8 electrochemical cell. So here on the left, we had they prepared a wafer with 64 electrodes. This wafer was then placed into a gasket, and this gasket was then placed into an electrochemical cell in which they were able to provide the liquid for either sequential or semi-parallel operation, so 1 by 1 or 8 by 8. Sorry, 8 at a time operation. Alkaline water splitting was used as the probe reaction, and it was operated under industry relevant screening conditions. So just to demonstrate what the setup looked like, the wafer was placed inside the VSP P1 nanostructured materials printer, and there were two G1 nanoparticle generators that were connected to the printer. The first one was equipped with nickel electrodes, the second one was equipped with iron electrodes. And by varying the total power or the relative power output between the nickel and the iron nanoparticle generators, we were able to control the nickel and iron ratios within the final electrocatalyst. In addition, by varying the deposition time, we could control the layer thickness, and the electrochemical cell was then used for the oxygen evolution reaction with 30% KOH solution and a current density of 200 milliamps per square centimeters. So here is again our, or the cell, the wafer that was placed in the printer. The results that we obtained from this in the oxygen evolution reaction, here on the left, we show how the nickel content influenced the cell potential. On the x-axis, we have the nickel content, and on the y-axis, we have the cell potential. And what we found was that at lower nickel content, we got a lower overpotential, which then meant that we had a more efficient electrocatalyst. On the right, we demonstrate how deposition time influenced the cell potential. And what we found was that there was indeed an optimal layer thickness at which we had the lowest overpotential, meaning that somewhere there was an optimum or an optimal electrocatalyst. If we superimpose these two plots onto each other, we get something like a 3D plot, where on the x-axis we have our nickel composition, on the y-axis we have the deposition time, and this color scheme shows the cell potential, and as we go from light green to dark blue, we get to lower cell potentials, meaning that we have a more efficient electrocatalyst. And in this proof of principle study, we found that indeed that the iron-only catalyst yielded the lowest overpotential, but that there was an optimal iron layer thickness to achieve the optimal catalyst. Now, overall, what this demonstrated was that we were able to synthesize electrocatalysts in high throughput and screen their performance in the oxygen evolution reaction in high throughput as well. So to summarize this presentation, I've demonstrated how a single sample can easily be prepared using the VSP G1 nanoparticle generator equipped with the VSP A2 filtration accessory. And I've also demonstrated how we can accelerate electrocatalyst synthesis and screening using the VSP P1 nanostructured material printer. And with that, if you would like to look at any of our previous webinars, you can find them on our website. If you're interested in reading up on these applications as well, you can find them on our website at vsparticle.com/applications. If you feel inspired by this webinar, feel free to request a demonstration to try out the equipment for yourself. This can be done by filling out the demonstration form at vsparticle.com or by emailing us at demo@vsparticle.com. And for anyone who's interested in sales information, please contact us at sales@vsparticle.com. With that, I'd like to thank you, and I'd like to open the floor to any questions.
Thank you, Wilbert, for this insightful presentation, and thank you everyone for attending this webinar. We will now proceed to collect your questions and answer them. Please give us a few moments. First question: how can we control the particle size and the metal loading?
So the particle size can be varied by varying the gas flow, the current, and the voltage. But the most, let's say, effective way to really vary the particle size is with the gas flow that you use. So by increasing the gas flow, you decrease the residence time of your ablated material in the reactor head, which means that you get less aggregation of your nanoparticles, of your vapor, which means that you get smaller nanoparticles, and vice versa. If you increase the residence time by using a lower gas flow, you're able to obtain larger nanoparticles. And then the second part of that question, I think it was, how do we control the loading? So this is essentially just determined by deposition time. So a higher loading is achieved by depositing for a longer period of time. But let's say the most important part there to also take into account is that each element has a different ablation rate. So you have ablation rates within the range of milligrams per hour. But after anywhere between a couple of minutes to a few hours, you're able to obtain reasonable loadings on your felt.
Thank you. We are moving on to the second question. What is the most promising approach to prepare alloyed nanoparticles?
So this is something that I'd also shown in one of the slides. Let me see if I can find it again. We go here. Yep. So the most effective way of doing this is by you can either mix and match electrodes, as we do here in a single G1 nanoparticle generator. But what you'll get is a mixture of compositions in your final nanoparticles. And then the most effective way to really get alloyed nanoparticles is by having your electrodes pre-alloyed. And then using those electrodes to generate your nanoparticles.
The third question, what does a demonstration include, and do we need to pay for it?
So yeah, no, this is a nice one then. So the demonstration is basic. How it would work is that you would first contact us, and we'd try to find out what kind of equipment is best suited for your application. And then based on that, we'll plan in a demonstration. So for a couple of the electrocatalysis groups that we've worked with, we've then brought the VSP G1 nanoparticle generator with the filtration accessory because we were depositing on porous materials. The overall demonstration would include us coming to your facility, installing the equipment, teaching you how to use it, and then you depositing the nanoparticles on the substrates that you're interested in. And in general, we leave it at your institution for about a week. And what's important is that we don't charge for this. Within our territory, we go there to showcase the equipment to you, and we really want you to get a feel for what the equipment does and what you're able to achieve with it to see how well it works for you.
Thank you, Wilbert. Moving on, what is the maximum particle size that can be obtained? Is it possible for a range up to 100 UM?
Okay, so 100 micrometer would be I think that might be 100 micrometer nanoparticles as individual particles. Sorry, 100 micrometers is no longer a nanoparticle, but that spot size is possible. So we can print that spot size. When it comes to varying the particle size itself, the largest primary particles are below 20 nanometers, but there are tricks when using this approach to prepare larger nanoparticles, but this would require some additional components, such as furnaces, for example. But it is in principle possible to get to particles that are larger than 20 nanometers, but you would need to include something like in-flight sintering to achieve that. But something like 100 micrometers, that's really then that would fall into the category of printing or depositing using impaction. And that spot size, I think, is something that we can achieve. I think that's the lower end of our spot size.
How does the size of the electrode affect the particle generation? Is the distance between the two electrodes maintained constant as it is consumed with time?
So in one of the in our reactor head, on one of the end caps, there is a little motor that then moves one electrode closer to the other. So indeed, as you start ablating the electrodes, they'll get shorter, but then this motor will ensure that the distance between the two electrodes remains constant. So if you have particularly short electrodes, it will calibrate for that at the beginning, but there is a maximum size of the electrodes, and I think that's around 2.5 centimeters.
Thank you. Is the structure of the nanoparticle the same as that of the electrode?
This depends on what you mean by structure. So composition-wise, yes, but you are really preparing nanoparticles, and the let's say the crystallinity of these nanoparticles is also down to the size of the nanoparticles that you obtain, and whether or not you've done any thermal treatment downstream. So composition-wise, the nanoparticle composition is the same as your electrodes, but structure-wise, it's really the difference between bulk versus nanoparticle.
Thank you. I think we have time for 2 more questions. How do you take care of the contamination from previous depositions? The produced nanoparticles will certainly deposit on the inside of the generator. Do you need to clean it every time?
Good maintenance would mean that you just need to wipe the inside chamber. If you're using the same electrodes, you can continue generating nanoparticles for a couple of hours. If you then decide to switch electrodes, then of course you'll need to clean the chamber to prevent contamination. This is just done with paper towels and a solvent of sorts, so ethanol, isopropanol, or acetone, or water. The entire inside can easily be accessed and cleaned. And for, let's say, the most stubborn nanoparticles, most of the reactor head can be placed into a sonication bath to remove any nanoparticles that might still be in there. But in general, wiping it clean is sufficient.
Thank you, Wilbert. And now we are at the last question for today. Can we use this generator for metal, inorganic, organic hybrid materials?
So something, how I hear this question now is, can we use this for something like MOFs or encapsulating the nanoparticles in some form of carbon? I think this is something that we could look at, but it's really something that we should discuss offline.
Okay, we will follow up with this answer via email. Unfortunately, our time is up for today. I would like to thank everyone for joining, and especially Wilbert for this insightful presentation. I hope everybody found it interesting, and if this is the case, please follow up with us through our demonstration or at sales information. We will leave the event open for 10 more minutes so that you can address all of your questions, and we will follow up with the answers in the coming days. Thank you so much for joining, and have a nice day, and I hope to see you all in our future online endeavors. Good day.